Hello everyone and welcome to our abstract algebra lecture on subgroups. Let's get right into the preliminaries. Given a group G with binary operator star and a subset H of G, H together with the binary operator star is a subgroup of G denoted H subgroup of G exactly when H together with the binary operator star is a group under that binary operation. And note something, I'm not sure if it's really understood or not, but let's make sure it's understood that the binary operation in the group G and the binary operation in the group H are one and the same binary operation. Now, given any group G and a binary operator, the group consisting solely of the identity element plus that binary operator, along with the entire group G itself, are always subgroups of G. G is said to be an improper subgroup of itself. All other subgroups are said to be proper subgroups. Now, let's look at some examples. Okay, our first example. The integers are a subset of the rationals, and the rational numbers are a subset of the real numbers. The real numbers is clearly a group. Add any two real numbers, we get a real number, so the operation is closed. Let's see, what else do we have to have? We have to have an identity, and 0 is the identity of the real numbers. And every element has to have an inverse. The inverse of an element x in the real numbers is negative x. So the real numbers are a group. Are these groups as well? I guess maybe we should show that they are. First of all, the rationals are closed under the operation of addition. We add any two rational numbers, we get a rational number. Okay, 2, 0 is the identity, and 0 is a rational number. And given a rational number q, its inverse is negative q, which is also a rational number. And for associativity, yes, given q1 plus q2 plus q3, this equals q1 plus q2 plus q3 Now, why is that? Essentially, it's because q1, q2, and q3 are not only rational numbers, they're real numbers. And associativity holds in the group of real numbers under addition. From now on, when this sort of thing happens and associativity is inherited from the parent group, I'll use that exact expression. I'll say that the operation is associative in the prospective subgroup because the operation is associative in the parent group. In other words, associativity is inherited from the parent group. Now let's check out the integers. Okay, 1. Z is closed under the operation of addition. If we add 2 integers, we get another integer. 2, 0, which is an integer, is the identity. And 3, given an integer n, its inverse under addition is negative n, which is also an integer. And for associativity is inherited from the rationals. So I just showed that the integers are a subgroup of the rationals. I could show also that the integers are a subgroup of the real numbers under addition, but I'd rather state it in a different way. We might note this once and for all time. The property of being a subgroup is transitive. So if group K is a subgroup of group H, and group H is a subgroup of group G, then group K is a subgroup of group G. And so we can apply that to the example that we just had. We know that the integers under addition are a subgroup of the rationals under addition. And the rationals under addition are a subgroup of the real numbers under addition. Hence, the integers are a subgroup of the real numbers under addition. And this is very much transitive in the same set. Being a subgroup is transitive in the same sense as being a subset is transitive. What about the integers? Do the integers under addition have any proper and non-trivial subgroups? What do I mean by non-trivial? The group consisting solely of the identity is always a subgroup, but we know that. It's trivial. The group consisting solely of one element, having the identity, is always going to be a subgroup. It's trivial. We're looking for non-trivial and non-proper, or rather, we're looking for non-trivial and proper subgroups of the integer. And the answer is, yeah, there are some. This is exactly what it looks like. The number 2 times z, the symbol for the integers, 2z under addition. And what this is the set of all multiples of 2. Under addition. And we could also denote it this way. This is a subgroup. And let's put it to the test. Is it closed under addition? And the answer is yes. 2m plus 2n, where n and m are integers, is equal to 2 times m plus n. And m plus n, of course, is itself an integer. So we take two even integers, two integer multiples of 2, we get another integer multiple of 2. So let's see, another one. Does it have the additive identity? Looks good. Okay, we have closure, we have identity, we have an inverse. So given 2n in the set 2z, its inverse, which is negative 2 times n, is also in 2z. The inverse of an even number is the negative of that even number, which is also an even number. And associativity, the answer is yes. And we can say it's inherited from the integers under addition. So here's an example of a subgroup of the integers, non-trivial, non-trivial and proper. Are there other subgroups of the integers? And the answer is yes. Let's look at a few. We'll be seeing more of these. We have a bunch more subgroups of the integers, as we're about to see. Infinitely many proper, non-trivial subgroups of the integers. For example, 3z. This is the set of all integer multiples, or all whole number multiples of 3. And notice that 3z is a subset of the integers. And notice also that if we take two multiples of 3, we get another multiple of 3, so the operation's closed under in 3z. The 3z is closed under the operation of addition. 0 is the identity, and here I've actually listed the number in inverse pairs. 3 and negative 3 are additive inverses. 6 and negative 6 are additive inverses. Associativity is inherited from the parent group, the integers. So this is definitely a subgroup of the integers, as is 4z and 5z. and in general NZ. Now, considering that we actually have, in general NZ, yes, and I need to complete this statement. Tell you what, we'll just restrict this to the integers, natural numbers rather. For all natural numbers n, NZ is a subgroup of Z. Now, I guess the next question is, how do all of these things fit into the subgroup scheme? How do they relate to one another? We're going to have to define something called a lattice diagram to answer this question. To investigate the subgroup structure of the integers under addition, we're going to define something called a lattice diagram. A lattice diagram is a diagram that displays the subgroups of a group G. A line segment leading downward from G to H indicates that H is a subgroup of G. And here we have that. We have a line leading downward from group G to group H. That tells us that H is a subgroup of G. Similarly, a line segment leading downward from group H to group K indicates that K is a subgroup of H. And here we have that shown schematically. We have a line leading downward from group H to group K, and that tells us that K is a subgroup of group H. Now, remember, the property of being a subgroup is a transitive property or a transitive relationship. So let's make sure that we note that well. Okay, check out this lattice diagram. From this part, we get that group H is a subgroup of group G. And from this part, we get that group K is a subgroup of group H. Yeah, I guess we can see that. But let's note also, since the property of being a subgroup is transitive, K is also a subgroup of G. So anytime we see a lattice diagram from group to subgroup to subgroup, this is a subgroup of the parent group. This is also a subgroup of the parent group and a subgroup of the group directly above it. Now, let's show a partial subgroup structure of the integers under addition. And I say partial because the integers have infinitely many subgroups. We can't show them all. We can only show a few. So essentially, we'll give a partial answer to the subgroup structure of the integers using a lattice diagram. Okay, lattice diagram of the integers, here we come. And we noted that 2z was a subgroup of the integers. 3z is a subgroup of the integers. Neither of those two subgroups are subgroups of either each other. 2z is not a subgroup of 3z, 3z is not a subgroup of 2z, but they are both directly subgroups of the integers. So here's what I'll do. I'll acknowledge 2z over here, and over here I'll acknowledge 3z as a subgroup. Now, 4z is a subgroup of 2z. Every multiple of 4 is also a multiple of 2. And I don't think there's any subgroup in between them. As a matter of fact, I'm sure that there aren't. Now we can do the same thing with 3z. 6z is directly a subgroup of 3z. Every multiple of 6 is also a multiple of 3. And we can also do 9z. 9z is also a subgroup of 3z directly. There are no subgroups in between these on the lattice diagram. Now let's see, am I leaving something out? Yeah. I guess over here I'd put 5z. See, the diagram's getting so big now, I'm going to have to start leaving subgroups out. I'm going to leave 5z out. If I put it in, it would be over here or maybe over here. I guess it would be over here. 5z is directly a subgroup of z. So any prime number times z is directly a subgroup of z. Now. 8z is directly a subgroup of 4z. Nothing in between those two on the lattice diagram. 12z is directly a subgroup of 6z. Holy moly, where is all of this going? You know something? I am going to have to put some more line segments in here. Isn't it true that every multiple of 6z is also a multiple of 2z? Or I'll tell you what, I'll draw it a little bit better. Okay, 6z is directly a subgroup of 2z. There's nothing in between. And you know what? 12z is directly a subgroup of 4z. Every multiple of 12 is also a multiple of 4. So let's do that. Holy moly. Holy moly. Now, what about subgroups of 9z? I can double this and get the subgroup 18z. What kind of interesting things happen if I do that? 18z is directly a subgroup of 9z. It's directly a subgroup of 6z also. Every multiple of 18 is also a multiple of 6z. Holy moly, this is getting complicated. I tell you what. And let's see, down here I have 16z. Whoops. 16z. 24Z here. Oh my goodness, what am I doing? 24Z. And you know what? Every multiple of 24 is also a multiple of 8. Holy moly, holy moly, holy moly. And let's see, 36Z is directly a subgroup of 18Z, also directly a subgroup of 12Z, and indirectly a subgroup of 4Z. And holy moly, we can go on. We'd put 5Z here, 7Z here, and so on. So this is a partial lattice diagram of the subgroups of the integers under addition. And I think in future examples, we will on occasion use lattice diagrams to show the subgroup structure, especially for finite groups that have finitely many subgroups. Recall this, given a group G and an element X in G, the set of elements of G that are generated by X is denoted this way. And this represents the set of elements generated by X. So essentially, using additive notation, the set of elements generated by X equals all integer multiples of X, again, using additive notation. And the set of elements generated by X is always a subgroup of G. And here's why. Nx, that is X added to itself n times, is always an element of G because G is closed under the operation of addition. Also, since the inverse of X, namely negative X, is in G, negative n times X is the same as n times negative X, and that's an element of G also for all n. So, what this means is that all natural number elements of X are contained in G. And not just that, but in fact, all integer elements of X, integer multiples of X, are contained in G also. And as we'll see, that goes for 0. 0 is the identity, and 0 is an integer multiple of X. It's contained in G. And that's true, but that's not what I wanted to say. I wanted to say that it's contained in the set of elements generated by X. And you know, that's I'm showing that X is a subgroup of G. Excuse me for a minute, please. I beg your pardon. I don't know what I was thinking, but let me backtrack. The set of elements generated by X is indeed a subgroup of G, always. The first thing that we want to notice is the set of elements generated by X is closed under addition, or under the group operation inherited from G. If we have any integers m and n, then mx and nx are both elements of the set of numbers generated by X, just by definition of this set. And if we add the two things together under the group operation, we get m plus n times x, and m plus n is an integer. So if we take two integer multiples of x, we get an integer multiple of x. So this is in the set of elements generated by X. So the point is that the set of elements generated by X is closed under the group operation addition. 0 is the identity, and 0 is an integer multiple of X, namely 0 times X, and 0 is contained in the set of elements generated by X. So I'll note the identity 0 is an element of the set of elements generated by X. The inverse of nx, namely negative nx, is generated by X. If n is an integer, then negative n is an integer. So negative nx is contained in the set of elements generated by X. And associativity is inherited from the parent group G. So the set of elements generated by X is always a subgroup of G, the group that X came from. Now let's look at some more examples. Z6 under addition modulo 6. Let's see. 3 plus 3 is 6, which is 0 mod 6. And 3 plus 0 is 3. It looks like the element 3 just generates itself and 0. And the operation is addition modulo 6. So this is a subgroup of Z6 under the operation of addition modulo 6. The set of elements generated by 3, this is it, forms a subgroup of Z6. Let's look at another example. Let's see what element 2 generates. Two plus 2 is 4 mod 6. 2 plus 4, or tell you what, 2 plus 2 plus 2 is 6 mod 6, which is 0. 2 plus 2 plus 2 plus 2 is 0 plus 2 is 2. Okay, so 2 generates the elements 0, 2, and 4 mod 6. And that is a subgroup of Z6. And let's check out 4. The element 4 what does 4 generate? We'll see. 4 plus 4 is 8, which is 2 mod 6. 4 plus 4 plus 4 is 2 plus 4 is 6, which is 0 mod mod 6. 4 plus 4 plus 4 plus 4. This is 0 plus 4 is 4 mod 6. So the element 4 generates 0, 2, and 4. Same subgroup as up here. Now let's see, what are the other elements of Z6? 0, of course, just generates the group that contains 0 and nothing else. Since 1 and 6 are relatively prime, this generates Z6. So if we left anything out, 0, 1, 2, 3, 4, we've left out 5, haven't we? Okay. Since 5 is relatively prime to 6, 5 is going to generate Z6 also. So let's draw the subgroup structure with a lattice diagram. Okay? Okay, let's draw our subgroup structure for Z6. Z6 is the same as the group of elements generated by 1 or the group of elements generated by 5. We also had the set of elements generated by 3. And the set of elements generated by 2. And 4, they're the same. So let's see, set of elements generated by 1, generated by 2, generated by 3, generated by 4, generated by 5. We've accounted for all of the subgroups generated by an element in Z6, except for the trivial subgroup. So there's the subgroup structure of Z6. Essentially, Z6 has 2 subgroups that are proper and non-trivial, plus 1 proper subgroup that is trivial. Let's do another example. We'll look at Z8, and I guess I should put the operation here, shouldn't I? Yeah, let's write it like this. And we're looking for the subgroup generated by the element 4, the subgroup generated by the element 2, the subgroup generated by the element 6. And I guess I deliberately picked all of the elements of Z8 that aren't relatively prime with respect to 8. So what does 4 generate? 4 plus 4 equals 8, but that's 0 mod 8. 4 plus 4 plus 4. This is 0 plus 4 is 4. Son of a gun. The only elements that 4 generates in Z8 are 0 in itself. Okay. And this is a subgroup of Z8. Next, let's look at Z8, but let's look at the subgroup of elements generated by 2. 2 plus 2 is 4 mod 8. 2 plus 2 plus 2 is 4, plus 2 is 6 mod 8. 2 plus 2 plus 2 plus 2, 2, 4, 6, 8, but 8 is 0 mod 8. 2 plus 2 plus 2 plus 2 plus 2, 2, 4, 6, 8, but that's 0. Plus 2 is 2. Well, I guess the elements that are generated by 2 are 0, 2, 4, and 6. That's the subgroup of elements generated by 2. And this is indeed a subgroup of Z8. Finally, let's look at the subgroup of elements generated by 6. So we have 6 plus 6 is 12, but that's 4 mod 8. 6 plus 6 plus 6, that's 6, 12, 18, but mod 8, that is 2. 6 plus 6 plus 6 plus 6, 6, 12, 18, 24. 24 is 0 mod 8, isn't it? 6 plus 6 plus 6 plus 6 plus 6. That's 6, 12, 18, 24, 30. But mod 8, that's going to be 6. So I guess 0, 2, 4, 6, those are the elements generated by 6 mod 8. And that's exactly the same as the group generated by 2. Okay. They are one and the same. And that is indeed a subgroup of Z8. Now we'll acknowledge that all of the elements of Z8 that are relatively prime with respect to 8, they're going to generate the entire group. So let's see, what would our lattice diagram look like? Z8, here's the parent group. And wow, these two are the same. And this is a subgroup of these two. Okay. So let's see. Group generated by 2 is the same as the group generated by 6. And the group generated by 4 is a subgroup of this. And did I leave anything out? What do you think? Am I missing something? The group generated by the identity, right? And so I'll write it like this. The set containing 0 under addition modulo 8. This is the lattice diagram showing the subgroup structure of Z8. And maybe just to acknowledge the others that are not, the other elements that are not specifically listed. 1, 3, 5, 7. All those elements of Z8 that are not relative. All of the elements of Z8 that are relatively prime with respect to 8 will generate the entire group. So that's 1, 3, 5, and 7. They're all relatively prime with respect to 8. As a matter of fact, son of a gun, they're not just relatively prime, they are prime in this case. But they will generate the entire group. More examples. More stuff. The group G is a cyclic group exactly when there exists an element X in G such that G, the group, is generated by this single element X. So a group is cyclic if the entire group can be generated from a single element in the group. And if this is the case, then the element X that generates the group is said to be the generator of G. Let's look at some cyclic groups, okay? Let's look at a lot of examples. The integers under addition. This is a cyclic group. With generators plus or minus 1. And the reason I can say this is because Z equals the set of all elements n times 1, for example, for n being any integer. And it also equals n times negative 1 for all integers n. So this is a cyclic group. The set of all integer multiples of 1 is the set of integers. The set of all integer multiples of negative 1 is the set of integers. So plus or minus 1 are the generators. Okay. 2Z. The set of all multiples of 2, all integer multiples of 2, is a cyclic group. What do you think the generators are here, huh? Plus and minus 2? That's right. So there's another example. Oh my goodness, what other examples can we come up with? I know. What about this? 3Z. This is cyclic. What are the generators? Plus and minus 3? You're absolutely right. Okay, let me generalize this. NZ for any N and Z. But you know what? Let me just restrict that to the natural numbers. This is cyclic. With generators plus or minus N. Okay, we got some good examples there. And I guess I would like to make an observation before I go on to more examples. Just an observation. All of these cyclic groups are subgroups of the cyclic group Z, the integers. This may mean something. It may not. All of these cyclic groups, 2Z, 3Z, NZ, are subgroups of the cyclic group Z. It may mean something. We'll remember this observation and see if it pops up again. Another example, the set of remainders modulo 6 under addition modulo 6. This is cyclic with generators 1 and 5. Those elements 1 and 5, which are relatively prime with respect to 6. So this group, Z6, is cyclic. And let me just insert something here. And now let's look at some of the subgroups of this generated by those elements that are not relatively prime with respect to 6. The subgroup generated by 3, I think we did that already, and it turned out to be just these two elements. But this is cyclic. Now let's look at some other elements as well. 2, and if I remember right, 4 generated the same cyclic subgroups, 0, 2, 4, under addition modulo 6. These are cyclic. And I should note subsets of Z6, which is cyclic. Okay. The parent group, Z6, is cyclic. Oh, let's see, I have one more subgroup, don't I? Yeah. The subgroup generated by 0. And trivially, that's cyclic. 0 generates itself, that's about it. And that's a subgroup of Z6. So we have the parent group Z6, which is cyclic, generated by 1 and generated by 5. And then all of the subgroups happen, in this case, to be cyclic. May mean something, it may not. We'll look at a few more examples. Yeah. Another example. The set of integers modulo 8, or the set of remainders modulo 8, under addition modulo 8. This is the set of remainders modulo 8, under addition modulo 8, is cyclic, and it has as its generators 1, 3, 5, 7. All of those elements, 1, 3, 5, and 7, that are relatively prime with respect to 8. So, Z8, this is a cyclic group. Let's look at its subgroups. Let's see. We worked with this, didn't we? 2 and 6 generate exactly the same subgroup. 2 generates 0, 2, 4, and 6 under addition modulo 8. Is a subgroup of Z8. And we'll just emphasize cyclic. Oh, let's see. We have 1, 2, 3. We're missing 4, 5, 6, 7. We're missing 4 and 0. Now 4 generates a subgroup. If we remember, it generated the subgroup having elements 0 and 4. This is cyclic. And it's a cyclic subgroup of the cyclic group Z8. And of course, 0 is going to generate itself and nothing else. But that's trivially a cyclic group and a cyclic subgroup of the set of remainders modulo 8. So again, something interesting. We have a cyclic group and all of its subgroups, and these are all of the subgroups, are cyclic. So that would lead us to make a conjecture Let's write down the observation first. Here it is, conjecture time. From these examples, we might conjecture that every subgroup of a cyclic group is also cyclic. This is true, and we'll prove that in the next lecture. Now, is the converse true? If a group is cyclic, is it necessarily true that every group that contains it is also cyclic? That's a good question. So let's look at it, and then we'll think about it for a bit. If a group H is cyclic, is it necessarily true that every group G that contains H is also cyclic? So if H is cyclic and H is contained in the group G, must G also be cyclic? Let's think about that. Can we think of a case where maybe that might not be true? And think about some groups that we looked at right at the beginning of this lecture. Right at the beginning of this lecture, we looked at the integers under addition, and they were a subgroup of the rationals under addition. And in turn, the rationals were a subgroup of the reals under addition. So do the rationals and the reals have to be cyclic just because the integers are? And how could we go about trying to discern the answer to that one way or another? Well, let's suppose it's true and see what happens. Are the rationals cyclic? If so, then the rationals are generated by some rational number q. And that is to say that the entire set of rationals is equal to the set of n times this element q, such that n is an integer. So the entire set of rationals is equal to integer multiples of this rational number q. We can get every rational number just by taking this one rational number q and multiplying it by the right integer. Is that true? No. And some of my students were sharp enough to figure this out, and I was well pleased with that. Consider this element q over 2. Q is our prospective generator. Consider q over 2. Q over 2 is a rational number because it's the quotient of rational numbers. And yet, q over 2 is not equal to n times q for any integer n. This contradicts the fact, or the assumption, that this one rational number q generates the entire set of rational numbers. Well, we get a contradiction. Hence, the set of rational numbers under addition is not cyclic. And that means that the real numbers are not cyclic either. Because if the real numbers were cyclic, every subset of the real numbers, including the rationals, would have to be cyclic. So the integers are cyclic, the integers under addition are cyclic, but a group that contains them, the rationals under addition, are not cyclic. So it's not true that if we have a cyclic group contained in another group, the larger group has to be cyclic also. That's just not true. Well, that will conclude this lecture. We'll have another one coming out in about a day or two.